So we have one more example in this section that's going to, again, demonstrate how we can use our central limit theorem. So example 2 says, the average length of maternity stay in a U.S. hospital is said to be 2.4 days with a standard deviation of 0.9 days. We randomly survey 80 women who recently bore children in a U.S. hospital. So A says, what is X and how is it distributed? So, right, we're looking at the average length of maternity stay in a U.S. hospital. They said, right, X is distributed. Now, they don't say whether it's normally distributed or not, right? So we can't really say what the distribution is. We don't know what it is, and we can't guess. But it does have a mean, right, of 2.4 and a standard deviation of 0.9, right? So that's what we know about, right, the average length of maternity stays, but we don't know really if it's normal or not. Now, X bar, right? So again, right, this is our sampling distribution. It is distributed, right? Is it normally distributed? Well, our central limit theorem states that if the initial distribution was normal, then yes, the sampling distribution would also be normal. But this isn't the case because we don't know if the other population was normal. So we then can look at the other case, which is as long as it's a large enough sample size, then the sampling distribution of sample mean should be normally distributed. And in this case, right, our sample size is 80, right, which is greater than 30. So the sampling mean should also, the sampling distribution, sample mean should also be normally distributed. So it would have a mean of 2.4. And then my standard deviation, so if I do this to the side, right, so my standard error would be the population standard deviation divided by the square root of n. So in this case, we would have 0.9 divided by the square root of 80. So if we just calculate that quickly, so 0.9 divided by the square root of 80. If it wants a decimal approximation, so 0.1006. So 0.1006. Okay, so that's how that would be distributed. So C says, can we find the probability that an individual woman stayed longer than 4 days? Why or why not? So we're looking at an individual woman. Now, individual woman, right, would be the distribution for part A. And we don't know if it's normal or not. So we can't really apply anything that we've learned thus far. So we would say no, since we don't know the distribution of the population, we can't find this probability. Okay, so if we knew it was normal, then we could go and figure out this question. But since we don't know the distribution of the initial population, we really can't find this probability of this individual woman. Now, D says, what is the probability that the average stay for the 80 women is longer than 4 days? So the average stay, right, they're talking about the mean would be 80. So this would be part B's distribution, right? So this we can actually find. So they want to know the probability, right, that the sample mean is greater than 4. Okay. So if I draw my picture here, right, so we know that the mean, right, was 2.4. Right, the standard deviation is 0.1006, so it's fairly small. So 4 is probably going to be way out here somewhere. And it says more than. So my normal CDF would be the lower limit, which would be 4. Upper limit, again, is going to positive infinity, so 99,999. My mean was 2.4, and my standard deviation was 0.1006, right, my standard error. All right, so if I hit second distribution, get my normal CDF, we're going to change that to 4, 99,999. Mean was 2.4, right, and my standard error. So you could, again, if you want, probably the most accurate is just to go through and type the 0.9 divided by the square root of 80, or you can approximate, which is what we did, 0.1006, we'll paste that, and we'll get, right, roughly, right, this value here is roughly 0, right? It's not, I guess, exactly 0. There are some decimals, but it's roughly 0 for our case if we round. So the probability of this happening is nearly impossible, okay? All right, so our last letter, E, says, what is the probability that the average day for women, 80 women, is between 2 and 3.5 days? So they want to know the probability, right, that it's between 2 and 3.5 days. Okay, so let's see here. So if I draw my picture, right, so I have 2.4. I have 2, right, which maybe is here, 3.5. So it's going to probably be, right, we're going to shade probably most of the curve here. Okay. So we'll have our normal CDF. My lower limit looks like it's going to be 2. Upper limit's going to be 3.5 in this case. And then I'll still have the same mean and standard error from the last question, right? So I'll have seconds and vars to get my distribution. Normal CDF. So lower limit is 2. Upper limit is 3.5. Mu is 2.4, right? Standard error is the same, so we'll paste that. And so this probability here, right, is roughly, right, if we round, roughly 1. So we're almost guaranteed for this to happen, right? I guess if you kept 5 or 6 decimal places, it wouldn't be exactly 1, but approximately. So again, this example is just, again, how we can use that central limit theorem, even if we don't know the distribution of the initial population. All right, so this is how we can use our central limit theorem.